All right, so yeah, I think we can start now. So good afternoon, everyone, and welcome to our first seminar with the title Optimization-Based Solution for Control and State Estimation in Dynamical System. And today we will be looking at the mobile robots as an example of a dynamical system. For those who don't know me, my name is Mohammed, and I'm a postdoc fellow in MME here. So I divided the presentation over 3 parts. In the first part, I will be talking a little bit about optimization, just a brief introduction to optimization and the kind of optimization problems we are after today. I'll give also a couple of examples on like very simple optimization problems and how to solve them using the software we're going to use today, which is called Casadi. Then in the second part, I'll talk about model predictive control, which is an optimization-based technique for control. I'll talk about its problem formulation and then how to implement it for mobile robots as an example for a dynamical system using, of course, Casadi. And in the last part, I'll be talking about moving horizon estimation, which is a state estimation technique that is based on optimization. And again, we're going to apply MHE for a mobile robot. And it turns out that we will recycle actually most of the things we will learn in the implementation of MPC in the implementation of MHE. Right? So since we are talking about optimization-based solutions for control and state estimation. So why do we do optimization in general? So generally we do optimization because it has many applications in business, for example, for resources allocations and logistics. Also in science for fitting system models to data. In machine learning, for example, you get some training data and you would like to fit some model to this training data. And also in engineering for designing of technical systems, like designing machine parts in mechanical systems or probably electronic parts in digital systems. And any optimization problems actually is characterized by 3 main elements or components. The first one being an objective function that we would like to either minimize or maximize. So for example, if we're looking at a curve fitting problem that we want to solve by optimization, we would like to minimize the difference between the model we're using, the output of the model, and the training data, right? That's something we want to minimize. In a finance problem, if we have an objective to maximize profit, so this means that we have an objective function that we would like to maximize, right? So as you can see, the optimization function has a variable called W, and we call this variable the decision variable, or sometimes the optimization variable. This is the variable that when we manipulate, we basically manipulate the value of the objective function, right? Sometimes also we can have constraints on the optimization variable or a function of it. These constraints can be equality constraints or inequality constraints, right? By the way, during the presentation today, feel free to stop me at any time if you have a question, right? Okay, so then what would be the mathematical formulation for an optimization problem? It turns out that there are different mathematical formulation for optimization problems, but the one that we are after today, and it's actually a generic form of optimization problems called nonlinear programming problems, or NLP. And in a nonlinear programming problem, this is how we write down our optimization problem. We simply say that we would like to minimize an objective phi using or by manipulating the optimization variable W, while we have some inequality constraints and equality constraints that we would like to satisfy, right? So this is how the nonlinear programming problem looks like in general. And we also have the assumption that these functions phi, g1, and g2 are usually assumed to be differentiable functions. Actually, NLP is a general class of optimization problems where in some cases can be reduced to other special cases. For example, if the functions phi, g1 and g2 are affine, and affine means that they are linear combinations of the optimization variable, the problem turns out to be a linear programming problem. And in the case that the g1 and g2 are affine, but the objective function is quadratic, the problem turns out to be a quadratic programming problem. So linear programming and quadratic programming are sub-problems or are already covered if we already know how to solve a nonlinear programming or problem or an NLP, right? There could be other variants as well, right? So knowing how to solve NLP, that's good to know, or actually good to practice. And turns out that this is enough to implement MPC and MHE, at least for the examples in this lecture. All right, so we said that we sometimes want to minimize an objective or maximize an objective. So in case of minimization, this is how our optimization problem is formulated. And in case of maximization, it turns out that maximization is equivalent to minimizing only the negative of the function. So if we know how to minimize, then we know already how to maximize, right? So we have an objective and we want to maximize it. We simply minimize its negative, right? All right, so that's one thing. The second thing is sometimes we could have a global minimum for a certain objective function or a local minimum. So for example, here we have a sinusoidal function that is enveloped by an exponentially increasing function. So that's why we have this increasing oscillations, right? And for this minimization problem, we would like our optimization variable to be between this range, 0 and 4 pi. So in this case, if we look at the optimization problem, we will see that the absolute minimum, or in other words, global minimum, is actually this point down here. But at the same time, we have multiple of local minimum. So in this case, we have 3 local minimums, and one of them is actually a global minimum, right? Today we're actually focusing on finding the local minimum or the local minimum solution for the optimization problem, because solving for global optimization is in general not straightforward and time consuming. And if we talk about control and state estimation, real-time applicability is a question for us, right? And turns out for our purposes in this workshop, having a local solution is enough, or is actually sufficient. All right. So now we know that this is how the optimization problem looks like. So what happens if after we solve it? What is the solution? So the solution, we can refer it to as W star. So the value of W at which the objective function is minimum. So mathematically, we can write this as W star equals to arg min, or the minimum argument for the minimum, for the objective function phi. So basically, if we take this W star and plug it back to the optimization objective or the objective function, we will get the minimum of that objective function, right? In general, we are interested in W star rather than the value of the objective at this W star, right? So let's go ahead and start with a very simple example. So say, for example, that we would like to find the minimum or the solution for the minimum for this objective function. It's a quadratic function in W. So we can write this problem as a nonlinear programming problem in which we would like to minimize this objective using or by manipulating the optimization variable W, right? So, so far we don't have any constraints, so this problem is unconstrained optimization problem. And actually, if you look at W in the objective function, so the objective function is quadratic in the optimization variable already, right? However, we will solve it using the NLP programming in general, right? Turns out that this function is actually, or this objective is actually very simple to minimize by simply finding the gradient of the objective function, equating that to 0 from calculus, right? And finding the value of W that makes the gradient or the derivative equals to 0, and this value is actually 3 in this case, right? So if we plot this objective function, here's our function, right? And here's the minimum of the function, and 3 is the value of W, the optimization variable, at which the objective function is minimum, right? Again, we are normally interested in the value of W rather than the value of phi at the minimum. However, in this problem, the value of the function at the minimum is actually 4. So 3 is the value of w that minimizes the cost function, and the minimum at this time is basically 4. Just as a side note, say for example that we would like to multiply the objective function as a whole by some constant, let's say 10, 20, or some constant, non-zero constant apparently, right? So what happens to this objective function? So the objective function will be lifted up a little bit or more, we don't care. When we solve this optimization problem, we'll get the same minimizer, but probably a different value of the function at that minimizer, right? So if you scale your objective function by just a constant, this doesn't change the minimizer, but it will change just the value of the cost function at the minimizer, right? So this is just as a side note, right? Okay. So now let's try to solve this problem using one of the softwares that I personally like and I personally used in my PhD, and I actually recommend it as a tool for those who would like to work on optimization problems in general. So the software is called Casadi, and I left up there the website which takes you directly to where to download it from and get things started, right? And Casadi, they have a very nice slogan which says, build efficient optimal control software with minimal effort, and that's what it actually does, right? And we will see how in this lecture, right? So Casadi has a general scope of numerical optimization, and we can use Casadi to facilitate the solution of nonlinear programming problems, the NLPs we just talked about. Actually, it facilitates the solution, but not solving the solution. So it depends on external solvers, and it turns out that if you just go to this website, download the package, the Casadi package, it comes with some pre-installed solvers for you. And it turns out that these solvers are basically enough for our purposes in this workshop, right? It's free and open source, that's a plus. And it's a project that started about 9 years ago, and its most recent version was released August last year. Casadi has 4 problems to solve, which are quadratic programming, nonlinear programming, root finding problems, and initial value problems for ODEs, or ordinary differential equations, and DEs, or differential algebraic equations, right? We are using it today basically for nonlinear programming problems. So let's go back to our problem that we would like to formulate in Casadi. So the installation of Casadi is very simple. You go to the Casadi website, you download the installation folder, you change the Matlab path to that folder, and bam, you're there, right? So let's see how to solve this optimization problem in Casadi. So I'll start by running directly my code in Matlab. So as you can see up there in the first line, I'm just adding the path to where the Casadi package is on my computer, and then I'm importing the workspace Casadi, right? Then I'm starting to define a variable. I'm calling it x in this case, and x is a symbolic variable with display name equals to or that is w, right? So sx, this function here, sx is a basic data type in Casadi that represents matrices with symbolic entries, right? So whenever I wanted to declare a symbolic entry, I simply use the sx.sim data type, right? Okay, then we define our objective, the variable obj. This is our objective, and objective equals to our basically the objective we saw in the previous slide, x squared, which is w squared minus 6x plus 13, right? So if we go to the command window in Matlab and write x, so this will print for us the value that is inside x, which is our symbol w, right? And if we go ahead and type objective in the command window of Matlab, we will get this symbolic expression of the objective. So far we have the objective expressed as a symbolic expression. So this is how Casadi sees it. So it sees w squared as sq of w, which is squared of w minus 6w plus 13. Right? So this is the symbolic representation that Casadi is based on. Right? Then we define a couple of variables. We're not going to use them for this problem, but we'll use them later today, like two empty variables, g and p. G is actually our constraints vector. It's empty for now, and p is the optimization problem parameter, which is again empty today. So not today, I mean for this particular problem. Okay, here I'm just redefining, or I'm defining a new variable, optimization variable, which equals to basically x, like my optimization variable, just giving it a different variable name, right? And then I'm defining a structure. This is how you define a structure in Matlab with 4 fields. These fields are f, x, g, and p. And this structure is called NLP prob, like stands for nonlinear programming problem, right? And it has 4 fields. These fields are my objective f, right? And my optimization variable x, right? And the constraints g and the parameters p, which are empty for now. So if you go to the command window and write NLP prob, we will see it as a structure with the objective as a Casadi data type, the same for x, and 2 empty variables g and p, right? So if you look at f here, so it says 1 by 1 Casadi, because it's a scalar, right? So it's a 1 by 1 matrix, right? And it's of Casadi type, or SX data type. Okay, so far so good. So now we will keep formulating our optimization problem. So we're defining a new structure. In Matlab, we'll call it opts, stands for options, right? And opts has some optimization tolerances for our optimization problem. And in this case, we're using a solver called IP-opt, or interior point solver. This is a standard optimization technique. And this solver is actually, again, open source. And we would like to just use these, optimization options, like the number of iterations we would like to have, the acceptable tolerance for optimization, and the acceptable change in the objective function, right? So you can find more details about the interior point optimizer for nonlinear programming problems in the IP-opt manual. It turns out that these functions are actually good for our purposes again today, right? So now we will see also something new in Casadi, which is the NLP sol class. So here we're creating an object called solver, and the solver is basically an object of the class NLP sol. That's a class in Casadi, right? And when we define this object, we define the solver that we would like to use. It's IP-opt in this case. We pass the nonlinear programming problem that we just developed in the previous slide, which has the 4 entries, the objective function, the optimization variables, g and p, right? And the options for optimization we would like to use in this problem, okay? Right. Finally, we apply the optimization, or we start the solver. So in Casadi, this is how the optimization problem is defined. So we have an objective function that is function of the optimization variable x and some optional parameters p, not used so far, right? We have some lower bounds and upper bounds on the optimization variable. That's for the cases when we have a constraint optimization. We'd like, for example, optimization variable to be within a certain limit. So in controls, optimization variable could be the control action. And in many cases, we would like this control action to be between some saturation limits, right? So these are the lower bounds and upper bounds on the optimization variable x. And optionally, we could also have some constraints, lower bounds and upper bounds on functions of this optimization variables, right? And optionally, parameters, right? So we are going to define some arguments for the optimization problem, again in the form of structure. So far we have 3 structures, right? NLP prob structure, and opts structure, and now the args or arguments structure, right? So in the argument structure, in the args structure, we define lower bounds and upper bounds on the optimization variable. So since this optimization variable is unconstrained in this very first problem, so the lower bound is minus infinity and the upper bound is infinity, unconstrained, right? The same for the constraints vector g, so we don't have constraints, so minus infinity to infinity. And we don't have any parameters, so I'm going to define a parameter field inside the args structure, and I leave it empty. And now I'm going to define an initialization for this optimization problem. So we said that it's a numerical, like IP-opt is a numerical technique for solving the optimization problem, so we always have to initialize with some initial guess for the optimization variable. So in this case, I'm going to initialize my optimization variable with an initial guess of minus half. Okay? Right, so now we're going to call the object we created, solver, right? And we're going to pass all these parameters. We're going to pass the initialization of the optimization variable, lower bounds on the optimization variable, upper bounds on the optimization variable. Okay, I'll open it for him. It's okay. Right? And then lower bounds and upper bounds on the constraints g. In this case, we don't have any. And the parameters, which is an empty again. Right? Right? So once we call this function, we get in this variable, sol, stands for solution, two fields, the field x and the field f. The field x is actually the optimal solution, the optimal solution for the optimization variable, like the minimizer value, right? So in this variable x sol, this is going to be my solution basically, right? And we get another field sol.f, which is the value of the objective function at the minimum, at this solution, right? So if we print out these values, we'll get the x, which is the minimizer, as 3, and the value of the cost function here will be 4. That's pretty much, or exactly what we had in the previous slide when we solved it analytically, right? So do you have any questions so far?
What's the difference? Matlab has optimized two paths.
What is what?
Matlab has its own optimization two paths.
Actually, yeah. For this, that's actually a good question. Like the difference between Casadi and the built-in optimizers in Matlab, like for example, fmin unc, like minimization for unconstrained problems, and fmin con, the optimization routine for constrained problem. It turns out that with help of Casadi and the external solvers, we can get much faster solutions. Like it depends on the size of the problem, but for like some problems that I tried both fmin con and Casadi, for example, I would say that I can get the solution 10 to 20 times faster using Casadi, than fmin con in Matlab.
How many cells? How large problems? Number of stages.
Yeah, like the number of control variables can be arbitrarily large because we're using the interior point optimization here, and this one is designed actually for larger scale nonlinear optimization problems. And I'll show you today an example on how large we can scale our optimization variables. Right? Okay, so far so good. So then few remarks for this particular problem. It's again single optimization variable. That was clear, and it was also unconstrained. And in our case, we had only one solution for the optimization problem. So this means that local minimum is the same as the global minimum. We had basically one minimum, right? So let's go ahead and try a second motivation example for using Casadi. So we are looking again at this objective function, sinusoidal times exponential function with these constraints. If we plot these functions, we see that we have three minimums within this range from 0 to 4 pi, right? And if we would like to solve this using Casadi, so here's the code right ahead. It's pretty much similar to what we did so far. The only differences would be the form of the objective function. Here we have this exponential function, right? We have the same options we had in the previous problem. The same class, NLP sol, the same class in Casadi, the same options, the same even optimizer. But here the only difference are the constraints on x So here we would like our optimization variable to be between these two values, like to be lower bounded by 0 and upper bounded by 4 pi. And this is what we put here for lower bound x and upper bound x, right? Again, g, we don't have any use for g's. Like we don't have a function of x that is bounded. I mean a function of the optimization variable that is bounded. So these two fields will have the lower bound of minus infinity and upper bound of infinity, which means unbounded basically, or not used, right? Okay. We will initialize here by this value 1, for example. We will call our solver, and we will get the solution in the field x and the value of the minimum in the field f. But this particular problem has actually multiple solutions, multiple minimums. So if we minimize by 1, or we initialize, sorry, by 1, we will get the solution 0. Like the value of w that minimizes the cost function is 0. So starting from 1 here, the solver took me to here. So if we change the initialization to 4, for example, it will take me to this solution. And if we change it to another value 10, it will take me to that solution. So at all these solutions, you will see that the gradient is 0, right? At this solution, the gradient is 0. Then this solution, the gradient is also 0. But at this solution, the gradient is not 0, right? But we took this solution because that was the minimum that respects the constraints, because it's a constrained optimization problem, right? Okay. So any question for the second motivation example? Okay, sounds good. So the last motivation example, we have basically some data points that we would like to fit a straight line to it, right? So this problem is known as linear regression, and it's very widely used in machine learning for supervised learning, for example. So say, for example, like by machine learning language, we have this set of training data, and we would like to fit a straight line in it. So the straight line will have the form y equals to mx plus c, right? So in order to find the variables m, which is the slope of the straight line, and the y-intercept, which is c in this case, right, we would like to minimize the square of the sum of these errors here. And this method is called least squares method, right? So we would like to find the optimization variables or the values for m and c, so that we have we are minimizing this objective here, which is this objective. Here we have the difference between our output y and the predicted output from the input x, right? Okay, so if we would like to write this as a nonlinear programming problem, so we would like to minimize this objective over the two optimization variables. This time we have two optimization variables, and the objective is actually a sum. It's not just a function like in the previous two examples. It's a sum of functions, right? Okay, so let's go ahead and try implementing that in Casadi. So at the first part of the code, I'm just visualizing the data set that I have. So what I want you to remember from this slide are these two vectors x and y, which have the training data, the values for x and the values for y, right? So now we go to the second step where we implement Casadi. So we start by the regular stuff for Casadi, and we define here two optimization variables, two symbolic variables, which are basically my optimization variables, right? And now we start to create our objective. So in the previous two examples, objective was a simple expression, but here objective will be calculated over a sum. We will make the sum here by a for loop for like simplicity, okay? So our objective here, we have a loop over the length of the vector x, the number of data points we have, right? And for each step, we increment that objective by the new sum, by the new difference between the output and the predicted output, right? So now you can imagine how objective looks like if we want to print it on the command window, right? Because it's expressed as a symbolic variable, so it looks like pretty involved stuff, right? So here's the sum of all the terms we have in the sum here, right? Again, it's unconstrained problem, and we don't have any parameters that we want to include, right? So here's the optimization variable, and here's my structure, the first structure that has the objective function, optimization variables GMP, options for optimization and our object from the NLP solve class in Casadi, right? Then the constraints, again, unconstrained. So lower bounds and upper bounds on x and g are basically unbounded, right? And here when we initialize, we have to initialize by 2 values, not only 1 value, right? And that's so obvious. We call the solver and we get the solution in x, and x will have 2 fields. The first term in it is going to be our m, because that was the order we defined the optimization variables. We defined m, and the second one was c, right? And the second term is going to be my c, the solution for c, right? So in this case, this is going to be my slope, and this is going to be my y-intercept, right? And this min value, this is actually the value of the objective function at the minimum, right? Okay, so this is just a visualization of the result. Here's our straight line fitting these data points, right? And it turns out you would get exactly the same straight line from Excel, right? Because it's actually this least square method for this linear regression has a closed form solution. So we could have even solved it analytically. So, and you get basically the same result in Excel, right? Okay, one more thing that I would like to let you know about Casadi that will be helpful through the rest of the presentation today. And it's still related to the problem we just finished. Let's see how we define the objective for that problem. We define the 2 optimization variables, m and c, and then we define the objective inside this for loop, or we created the objective inside this for loop, right? And you remember how the objective looked like in the command window, right? So what if we have 2 random values of m and c, and we would like to find this objective? We have 2 options, right? The first option is we take m and c, and we go through the same for loop again. We do it, and we get a value of the objective. In this case, it will be directly a scalar value, right? And the second option is to use something built in Casadi, which is called the function object in Casadi. And this function object has many useful uses. We can actually use this object function to define a function. We give it a name, and we specify which input it takes and which output it gives, right? So this is how we define a function object in Casadi. So later, when we call this objective function and we pass these 2 parameters, 2 random parameters, it will give us directly the value of the objective for these 2 parameters, right? Was that clear? Okay. All right, so what I'm going to do here, I'm going to use this function to visualize the objective of our optimization problem. So think that in this optimization problem, for the linear regression, we had 2 optimization variables, the slope and the y-intercept, right? So if we have 2 optimization variables, this means that we still can visualize the objective, and it's going to look like a surface, right? Okay, so let's try a range of values for m and a range of values for c, and try all the possible combinations of these values by calculating the objective function at all these combinations, right? So when we do that, we will get this surface, right? So what I'm doing in this for loop basically is that I'm getting all the possible combination for m and c, right? And I'm calling this objective function, obj_fun here, and I'm passing these 2 values, and it returns to me the scalar value of the objective at these 2 variables, right? So here I used the function object in Casadi, right? So I basically calculated all these objectives, like at all the combinations of m and c, we calculated the objective, and that's how the objective looked like. It's convex. That's why, again, here, by the way, the local minimum is the same as the global. We have 1 minimizer. All right? Okay. If we look at this surface and we'd like to get the minimum, we will get this minimum, right? So we're getting the minimum from x and y, so we'll get this minimum, and this is very close to the minimum we got from solving that problem using Casadi. Of course, this one is approximate because we have a coarse discretization for the values of m and c, right? The objective of this slide is basically to introduce you to this function object in Casadi, right? And how we used it later here, right? So any question? No question? Then, okay, then that's it for the first part of the presentation. So now we go ahead and shift to the second part, where we'll talk about the optimization-based technique for control called model predictive control, or MPC. So what is MPC? And by the way, MPC is also called receding horizon control and sometimes moving horizon control. So let's look at what MPC is like by looking at this very simple single input, single output system, right? That it's in general a nonlinear system. It doesn't need to be actually a linear system, okay? So if we look at the this system through these two graphs, so we have here a graph for the control action U, and here a graph for the state evolution X. So far, these are the control actions applied so far. And this is how the state X evolved over the past, right? You will see X here continuous and U discrete, because we have the assumption that through this time step, the control action is piecewise constant, right? All right, so now we are at this time, K, and we would like to take a new decision or a new action so that our state X eventually reaches some reference X reference, or XR, right? So what do we do in an MPC or model predictive control is that we find we look in the future for n time steps, right? And we try to find the best or optimal sequence of control actions that we can apply or we can predict that makes the prediction for the state approaches or actually goes to the state reference. Right? So at this decision variable, we solve an optimization problem to get this hopefully optimal sequence of control actions to have the prediction of the state going to the reference. Right? Okay, and then what? And then we apply only the first portion of that sequence of control actions to the system. So when we apply this first control action and our current state is here, so we predicted that that state goes to this state, right? From here to there. But what happens in reality shouldn't be exactly as we predicted, right? So that's why in the second, after applying the first portion of the control action, we do another step of MPC and we get a new control sequence and we apply the first control action in that sequence. So in MPC, we have three things that we do. We do prediction, because we would like to know how this state X evolves. We do online optimization by minimizing the difference between this prediction and the reference by manipulating the control actions, right? And receding horizon implementation, we do this every sampling time or every time step, right? All right. So the mathematical formulation of MPC is very similar to LQR, which most of you are already familiar with. So we define what we call a running costs or stage cost, where we penalize the difference between the predicted state and the reference, and the difference between the control action and its reference value. For this case, the reference is 0. That's why I'm showing this difference as this distance, right? So this is called the running costs, right? And we are penalizing the second norm of these two differences, right? So that we are the error is always positive, right? And then we define what we call a cost function, which is a summation of this running costs over the prediction horizon, over all these steps, right? So we started with this these two differences. So now we're summing them up over all the prediction steps, right? So now the MPC problem can be formulated as an optimal control problem, where we would like to minimize that objective function by manipulating the optimization variable, in this case U, right? And this minimization problem is actually subject to a very important constraint, which is the relation between the prediction of x and the control action u, and it turns out to be our system model, right? We have another constraint on the initial value of the state in the prediction, which is the initial value of my state, right? The real state, right? Or the actual state. And I have some constraints on the control action that I should respect over the whole prediction horizon, and constraints on the state itself, which I also should respect for all the prediction steps, right? The last thing I would like to define here is the value function, and the value function is basically the minimum of the cost function at the solution for the minimizer u, right? We will not use, we're not going to use this value function today, but it's there for your reference, right? So do you have any question regarding the formulation of MPC? Okay, so let's keep going. MPC is actually one of the most, I would say, popular controllers now. Can be generally applied to multiple input, multiple output systems. Could be for linear systems or nonlinear systems, right? It has a natural consideration of constraints on the state x and the control u, approximately optimal solution. And it's been used in the industry since the 70s, requires online optimization, apparently. And there are some central issues in MPC. First of them is the stability issue. So here's our system, we'll apply MPC. What guarantees that the closed loop system will be stable? So that's one of the MPC issues, right? Another issue is how good is its performance? So you say that this is an optimal controller, then how do you measure the optimality of the solution, right? Or the optimality of the controller? How long does the prediction horizon should be, right? And finally, how to implement it numerically, right? And this is the main, our main scope for the talk today, right? All right, so let's go ahead and see how we will implement MPC for a mobile robot. Okay, so we're talking actually about a non-holonomic mobile robot, in this case a differential mobile robot. So this robot in general has 3 degrees of freedom. It's two degrees position degrees of freedom, x and y, and angular orientation theta, right? The differential drive robot or this non-holonomic robot has this kinematics model. So in this kinematics model, the inputs are the speeds for the right wheels and the speeds of the left wheels, right? This is a very simple non-holonomic kinematics model. R is actually the wheel radius, and D is the base width, like the distance between the 2 wheels, the wheels on the left and the wheels on the right, okay? And if we define our control variables as v and omega, or the linear speed of the robot and the angular speed of the robot, and the relation between them and the right and left speeds of the wheels is basically this equation, we will end up with this kinematics model, right? That's for holonomic a non-holonomic mobile robots. For a holonomic mobile robot, we would have 2 V's, because our robot now can move laterally. So we would have Vx and Vy and omega. But since this one is a non-holonomic, so the robot can move linearly in one direction, forward or backward, right? Okay, so here's our system. We have 2 control inputs and 3 states. This is how we can look at our system from input-output perspective. And if we look at the control objectives, we can possibly have a point stabilization control objective. Our robot is at some initial positions, and we would like to drive it all over to a goal position. And position means pose, position, and orientation, right? And we can also have the trajectory tracking problem. Trajectory tracking problem, we would like our robot to move along a time-varying trajectory, right? There's a third class of control problems called path following, where this timing or the timing law of the trajectory is not given a priori, but it's left as a degree of freedom for the controller to decide when to be where on the path or on the trajectory, right? So here's our control loop. That's the control system, the controller. We will assume that our sensors and state estimators work fine, and they feed us back with the full state, x, y, and theta. So now we are looking at the controller, which is MPC in this case. Right. All right, so now let's formulate MPC for our particular problem, the mobile robot, right? So first of all, I'll look at the system kinematics model, and then I'll discretize it, because we're going to do predictions, right? So we should use the model to do prediction for the state, right? In this case, I'm going to do predictions using the sampled form of the continuous time equation of motion, right? I use the simple Euler discretization technique. So here the new state equals to previous state plus delta t, or the sampling time, times the previous, like my right-hand side of this equation of the previous state and the control actions v and omega. So I just want you to remember that this is my equation, or the discrete time equation. The new state equals to previous state plus delta t times the this right-hand side. Okay, just keep this in mind, right? Okay, and then our optimization problem, or the MPC optimal control problem, we will get the running costs here. Then the summation of it gives us the objective function, right, that we would like to minimize for some admissible values for u, and we have these constraints. The first of them being the system model, right? Okay. Sounds good? So this is how the optimal control problem looked like for MPC. And so this is how OCP looks like, right? And this is how a nonlinear programming problem looks like. This is the standard form of an NLP that we saw how to solve it using Casadi in Matlab, right? Right, so our objective now is to see how to transfer or how to convert or discretize, more precisely, my optimal control problem to a nonlinear programming problem, right? We actually can use several techniques, single shooting discretization technique, multiple shooting, and collocation method. So in today's lecture, I'll talk about basically single shooting and multiple shooting, right? These are two very important concepts. Single shooting might be very intuitive to you. Multiple shooting may not, but it turns out that multiple shooting is much more efficient than single shooting, and you will see this by examples, right? Okay, so again, we're going to use the Casadi, right? So now we understand the structure of the problem, right? We have basically this optimal control problem, and we would like to solve it by transforming it to a nonlinear programming problem. And we know how to solve a nonlinear programming problem in Casadi already, right? All right, so let's go ahead and solve that on Matlab. Okay. So as usual, we will add the Casadi path namespace. We'll start defining these variables, the sampling time. So sampling time here equals to 0.2. And the prediction horizon length. And the prediction horizon here, I set it to 3. That's a fairly short prediction horizon. So 3 times 0.2, this means 0.6 seconds. So we predict only for 0.6 seconds, right? A robot diameter, not used here, just for visualization later. And here I'm defining the maximum and the minimum margins for the control actions on V and omega. Okay, so the maximum V should be 0.6 at max and minus 0.6 at minimum. And for omega, maximum is pi over 2 and minimum is the negative of that, right? All right, so now we will define 3 symbols for our 3 states, x, y, and theta, right? And we will define our states vector. We will call it state, and the number of states is 3. I'm just calculating that by Matlab, length of states. So this gives me 3 apparently, right? The same for the control actions, defining 2 symbols for the control actions, a controlled actions vector and the number of controlled actions. We will use this later in our code, so I'm setting up my code first. And here I'm defining the right-hand side of that equation here. If you remember that equation, this is my kinematics model. So here I'm defining this right-hand side, RHS. So RHS is basically a vector. The first entry is v cosine theta. The second entry is v sine theta, and the third one is omega, right? Okay. Nice. So let's define these variables as well. So the first one being a function. You remember the function object in Casadi. So this function, we defined 2 inputs for it and 1 output, which is the right-hand side. So what does this function do for me? When I pass the value of the state and the values of the controls to this function, it gives me this right-hand side, right? So if we go to the Matlab command window and we typed f.printDimensions, it will give me these outputs, that this function has 2 inputs. The first one of dimensions 3 by 1, which is my state, and the second input is 2 by 1, which is my controls, right? And the output is 3 by 1, which is my right-hand side of the kinematics model, right? Clear? Okay. Then we will define that vector, or this matrix, actually big U. So U has all the optimization variables for this problem. U has the control actions for all the prediction steps. We said that here we have n equals to 3, right? So we have 2 control actions, here and here, here and there, right? For these 3 steps, right? So this is how the control actions matrix U looks like in Matlab, and this is how it looks like in writing. Okay. All right, and then we will define a parameters vector. I'll call it P, or uppercase P, and P is of dimension 6. It has 6 entries, the number of states times 2, and this parameters vector will be later used to define my initial state, because every MPC is initialized every time step. So if every time I initialize MPC, I need to provide the initial state of the robot, or where the robot is at. And these last 3 parameters are the reference state for my robot, right? And finally, I'm defining the matrix, the big matrix X of SX type, of course. And it's a matrix that has 3 rows and n plus 1 columns. That's the prediction of the state, right? For each control action, how the prediction would look like. So the prediction will be stored in this matrix. That's clear? We will see how we will fill up these matrices now. Okay? If you have any question, feel free to ask me at any time. Okay? Right. So let's go to the next slide. So you remember what was in P. P has 3 parameters, right? And this big X is my matrix of the state prediction. The first column in it should be my initial value. When I start predicting the trajectory of the robot, I should start this prediction from some initial state, right? So the initial state apparently will be in the first column of X, capital X, right? And this state will be taken from the parameters that I will pass later to the optimizer. And these parameters are stored in the vector P, right? So what do you expect to see now in the first column of X? P0, P1, and P2, right? Okay. So now let's fill up the rest of the entries for X. So now we filled up this column, right? So now let's fill up the rest of the vectors. Okay? All right, what would be the next vector here? The next vector, or the next state, equals to the previous state plus delta t times the right-hand side of the kinematics equation, right? And that's what we are doing here in this for loop. So in this for loop, we extract the previous state from X, right? And we extract the control from the control matrix, right? We pass them through our function f. This function that gives us the right-hand side, right? So we say that the next state equals to the previous state plus delta t, or t here, right, times f value. That's the right-hand side, right? So what I'm doing in this for loop is that I'm basically integrating, starting from here, going to there, starting from here, going to there, and so on until I finish up this matrix, right? So the initialization was from my parameters, and the prediction was from my control actions and the previous state. We did this by forward recursion to fill up this matrix, right? Okay, here I'm just defining a function. I'm calling it ff, and this function takes as an input the control matrix and the parameters matrix and gives me the prediction, capital X. So once I know some solution for u over the whole prediction horizon, and I plug it in this matrix, this immediately calculates for me the prediction. So after this for loop here, if you go in Matlab command window and type X, you will see some fancy stuff here. It won't be just simple these. No, it will be a symbolic combination of P's, U's, and apparently T and the right-hand side of the equation. So it's going to be a pretty fancy, pretty involved matrix here, and it's all simples, right? So in order not to do this, every time I want to get the prediction, I'm basically defining this function here. So once I know the predicted control, I pass the predicted control to this function, and this returns to me the prediction for the state. Okay. And this is how the prediction of the state is like. So initial x0 comes here, then f of x0 and u0 goes here, and we keep doing forward recursion until we reach the end of it. So you can imagine how nonlinearly the last column in this prediction is. And even for like longer prediction horizons, you can like this is a function of a function of a function of a function, and this is all nonlinear propagation of these control actions through my prediction. Okay, sounds good. So far so good. Any question? Okay, so now let's go ahead and calculate our objective. We said that in calculating our objective, we should define some weighting matrices Q and some weighting matrix R for penalizing the deviation in state and deviation in control. So I'm just defining Q and R. Diagonal matrix with these diagonal entries. These matrices can be used later to tune your controller. So these are like the gains in a proportional controller, for example, like, right? Okay, and then we will now calculate or compute our objective. So we start with a zero objective, and we add up because objective is a summation now, right? So my objective equals to the difference between the state, which comes from the big matrix X that has the prediction of my states, right? Minus the reference, and we said we will store the reference in the second three elements of P. So we take here P from 4 to 6, from the fourth element to the sixth element, right? Transpose Q X, or this difference, right? Plus the control action, we take it from our control matrix capital U, right? Transpose R control, right? Straightforward, right? Okay, sounds good. So that's our objective. So now we have some constraints. So the constraints vector here, we will fill up this vector with some constraints. So imagine that your robot is in a map, and we would like our robot to stay within the margins of this map. So this means that we would like to add constraints on what elements in the state vector? X and Y, right? So we started this G vector as an empty vector, and then we will fill up this vector by entries from the prediction matrix X, capital X, right? So this is the capital matrix X. So what do we fill up this guy with in the end? We fill up it with these values here, right? So I take the first entry and the second, like from the first row and the second row for each column, which means for each step in the prediction, right? Sounds good? Okay. So far we defined P, G, and the objective, right? So now we can define our nonlinear programming problem structure, which has the objective calculated already, optimization variables, G, constraints, and P. Actually, the optimization variables I'm passing here has to be one vector, but we defined it as a matrix, as a 2 by n matrix, right? So we have to pass this as a vector, right? So what this reshape function does, that's a Matlab function, what it does is basically takes my U matrix and converts it to one vector, right? Just want you to know that U0 and U1, U0 is actually the linear velocity v, and U1 is the angular velocity w, or omega, right? Then here v, and that's omega, that's v, and that's omega. And when we put that as a vector, so the optimization variables became v omega, v omega, v omega, and so on, right? So the first two are the v and omega for the first time step, and the prediction second time step, and so on, right? We're defining here the object for the NLP sol object in Casadi. If we take NLP prop in the command window, we'll get this stuff here. So it has an objective that is 1 by 1, scalar. It has the optimization variables x. X is 6 by 1. These are my optimization variables. Don't confuse x, which is the optimization variable, with x, which is the state vector, with x, which is the x position of the robot. So lots of x's here, right? Okay, so x here is actually the optimization variable, this x, right? And it's 6 by 1, right? And g, the constraint vector, we said that we have n+1 state prediction, right? So we have 8 constraints. Each prediction we have x and y. So x and y, 2 times 4, that's the 8 by 1 in the g here, right? And finally, the p vector is 6 by 1, and we know the first 3 is my initial state, and the last 3 are my reference state, right? Okay, so now we define the arguments. It's again a structure. We have lower bounds and upper bounds on G. And what was in G? What was in G? The x and y position of the robot over the whole prediction horizon. So as we said, we would like our robot to be in a map that has a maximum x of 2 and minimum x of -2, and the same values for y. So I'm just setting the maximum and the minimum, or the upper bound and the lower bound for the states in x and y, right? And these parameters here, or these two arguments here, right? Now we're setting the maximum and the minimum for the optimization variable itself, or variables, right? Okay, so we said that our optimization variables is arranged as v omega, v omega, v omega, right? So the way we define the constraints here, I know that the initial optimization variable is v, and every second one, or every odd index in that vector is my v, right? So I'm going to the lower bound, and every odd index in this vector is basically v minimum, right? And every odd index in the upper bound, or for the upper bound, is v maximum, right? The same for omega, but it's every even index, and here every even index. I set my omega a minimum, or the upper bound and the lower bound, on the second optimization variable, or the second control action. Okay, that's my problem now, ready to be solved, right? Okay, so we will go ahead and start our simulation loop, right? So we're done with the formulation of the MPC problem, and we did not see any number so far, right? It's all formulated as simples. So you can imagine how fancy, for example, this objective look like. It would look like really fancy if you want to print it on the command window, right? So let's start our simulation loop. I'm defining here the initial position for the robot, xs, some variables, the reference. I would like my robot to go to this state. So the robot is starting from the origin, and I want to drive it diagonally to 1.5 meters in x, 1.5 meters in y, with the same initial orientation, right? So sometimes this is called parallel parking, right? Or, well, forward parallel parking, not exactly parallel parking, but yeah, right? I'm defining here a matrix that will store the value of x for each time step, like how the state x evolves with time in my simulation loop. Initial time, and here an initialization for the optimization problem. So here in this problem, how many optimization variables we have? To answer this question, we need to know how long the prediction horizon is and how many control actions we have. So apparently we have three optimization horizon of 3 or prediction horizon of 3 and 2 optimization variables. This makes up 6 optimization variables, right? Because we have, sorry, 2 control actions. Okay, so this makes up 6 optimization variables. So here we have, we are initializing this by a matrix of n rows, 3 in this case, and 2 columns. So this is a matrix with 6 entries, and it's all zeros. Just keep this initialization in mind now. Okay, we set the a maximum simulation time of 20 in this case, and a counter for the loop, right? And a couple of variables to store the predicted state and to store the control actions we will take. So our simulation will be pretty much in a while loop, and this while loop breaks after the simulation time ends or after reaching a certain error, like a certain closeness to the reference state. If my robot is close enough, then I'll break. And how close is close enough is basically this formula. That's how I measure how close is the robot is to the reference, right? Okay. Now remember, when we define the args structure, we always define a p field in it or a p variable in it, and p here has 6 terms, right? The first one is my initial state, and the second one is my what? The reference, right? Okay, and now we're defining the initialization for the optimization variable, and don't confuse x again with all different x's we talked about today. So x here is my optimization variable. This x0, don't confuse it with this x0. So this x0 is the initialization for the optimization variables, right? And we initialize the optimization variables by this u0 here. And it was a matrix, and here we're just reshaping it to be a vector, as what we did earlier, right? So our MPC problem is now solved just in calling this solver. Call the solver with these arguments. By the way, what arguments need to be changed every time step in this loop? Apparently, these 2 arguments. Every time step, the initial or the current position of the robot changes or actually updated. XS remains the same, so I could have just updated the x0. That's fine. And I can initialize the optimization variables by different initialization every time step, and we will see how. But for the very first time step, we initialized the control variables or the optimization variables by just zeros. Okay? All right, now we called so far we called our solver. So what would sol have? Sol have 2 fields. The x field, which has my optimal or my minimizer, like the optimal values for the control actions to minimize this objective function. I'm reshaping it to get again u as a matrix, because here sol.x gives me u as a vector, so I'm just reshaping it to get it again as a matrix, right? And here ff value, if you remember, this ff function gives me the prediction. Now I know some values for u. I want to calculate the prediction for x, right? You remember this function ff that we defined earlier, like in the 2 previous slides or something, right? So I'm just getting the prediction, caching or storing it in this 3-dimensional matrix. So for every time step, I have a prediction, and a prediction is a 2x2 matrix. So this makes up a 3rd-dimension matrix, right? So think of a 3-dimensional matrix as a book. Each page in a book is a 2x2 matrix, and each page is the 3rd dimension of this 3x3 matrix, right? So so think of the pages as the whole prediction every time step. So every time I turn a page, that's a new prediction. Every time I turn the page, that's a new prediction. right? All right. All right, and my control, I'm just storing here my control actions. I'm taking just the first term in U. We said that my control action will be always the first term in U. So far, we haven't applied this control action to my system. So, and we will do this in this shift function. So let's see what shift function does for us. Turns out that this shift function does two things. The first thing is, shift function, we propagate the control action in our function f and calculate the new state x, and this will be my new initial state for the next time step. That's why we call it x0 here. So initially x0 was this one. So once we are done with one loop here, x0 gets updated by propagating the control action through my system model, right? Actually, you do a second thing here, which is, you remember how we initialized the optimization variables here? By what? Just zeros, right? But now we have an optimal solution from a previous time step. Why don't we recycle it and use it as an initialization for the optimization variable for the next time step? This is what we do here. But we simply trim the first entry of it because we already used it. So we trim the first entry in U0, and we just repeat the last entry. This is our best guess about that entry, right? Right? OK, so that's the shift function. So after this step, we applied the control action, and we updated the initialization for U0 that will be used again here. Right? We update the counter, and that's it, right? I'm just here calling some visualization functions to see what's working, and let's do some demos on the on Matlab. So here I have my implementation here on Matlab. So this code will be given to you. I'll send an email with the link on how to get it, right? And just want to bring up Matlab on the monitor or the projector. And yes, so here you go. Yes. So that's my single shooting implementation. So again, you can see how large is my optimization horizon. So it's just 3. So the optimization horizon is just 3 steps. So let's run this. So these are my iterations that count down here. And this is how the robot approaches the reference. And this is how the prediction looks like. The prediction is actually very short, right? So the robot could not manage to go exactly to where I would like it to be. So one of the things that I can think of now is just increasing the prediction horizon length, right? So I have a good prediction of where the robot is going to be, okay? So the simulation here will terminate after the 20 seconds we set for the simulation time, all right? And these are the control actions. So you see that the maximum control action in V was 0.6, and that's something we are not going beyond, right? And the same for omega. That's one thing. Down here in the Matlab implementation, I'm calculating something called average MPC time per step. So that's basically the total simulation time of the loop divided by the number of iterations in this loop. This roughly gives me the average computation time per MPC step, and this turns out to be about 17 milliseconds in this case. The average is about 17 milliseconds in this case. So if I have a sampling rate of 10 hertz, which is 100 milliseconds, so I'm well below that number, right? For a mobile robot, 10 hertz is good enough, right? For low speeds at least, right? Okay, so let's now increase the prediction horizon length and set it up to 10. So the simulation will take a little bit longer time. So now you see a longer prediction, right? And the robot goes nicely to the reference position. Maybe not exactly, but that was good enough for the error tolerance we set, right? Okay, so let's now change the orientation of the reference. In terms of stability, this controller with this prediction horizon was enough to ensure that my system is stable. Like the robot goes exactly to where I would like it to be, right? Okay, so now let's just change the reference. So I'll go down here to the simulation loop. Here's my simulation loop. And I'm just going to change the reference, like to be the same position, but opposite orientation of the robot. So I set here the reference theta to be pi. Okay, and I'm going to run again my code. It turns out that a prediction horizon of 10 was not enough for doing that. So the robot goes ahead of my reference a little bit, and then it backs up as if it's parking, right? When you see this actually done on a robot, this looks really fancy actually on an actual robot, right? Okay, so in order to fix this problem, we can again increase the prediction horizon length. So the simulation would keep moving until we're done with the 20 milliseconds of simulation. So this notch here in the angular speed, that's when it turns and goes backward, right? So let's just increase the prediction horizon length. I think 15 would work here. I don't know. Of course, longer prediction horizon is reflected on longer simulation time or longer computation time, right? So here it backs up and meets my probably my my error tolerance, or no, maybe not. But it seems like not, because if it met, it could have stopped. Yeah, or it should have stopped actually. But this means that we increase the prediction. Okay, let me go back to the slide because it has the values. Oh yeah, so in this case, 25 would do the job, right? That's a pretty long prediction horizon, but that's fine. Okay. So do you have any questions so far?
How can we improve the dynamic constraints of the robot, such as the actual acceleration?
That's actually a very good question, and like how to put a constraint or how to penalize the rate of a change of the speed. That's basically the acceleration. So if you go to the cost function, we penalize the difference between the speed and the reference speed. And in this case, the reference speed is 0, right? You can also add an extra term to that cost function, which is the change in the speed, like the speed minus the previous speed, the current speed minus the previous speed. And if you put a good weight on that, this will make the acceleration and deceleration like slower than usual, or than without penalizing it. So instead of penalizing the difference between the control action and the reference, you penalize the change in the control action. I can show this to you on the slide. So I'm going to bring up the slides again. I'll go back. Oh, that's really bad. Yeah, here. So that's my running costs. So instead of penalizing this difference, or in addition to penalizing this difference, both can work, right? So you'll penalize the difference between u and the previous u, because think of it as that's a summation, right? So here I would put u of k minus u of k minus 1. See what I mean? And in the code, that would be right here. Oops. Yes, here. Here we're penalizing just the control action. So we get the control con here, right? So we could get con, right? And con minus 1, for example, or con plus 1, right? So we would have u of k and u of k plus 1, because index here doesn't start from 0. So if I'm starting from k equals to 1, I can say k minus 1. A 0 index doesn't work in Matlab, right? So here I can define con and con plus 1, and con plus 1 would be u of all columns, sorry, all rows, and k plus 1 column. And here when I penalize, it won't be just con, it will be the current control or the next control minus the current control action. I'm penalizing the change in the control, not the difference between the control and the reference control.
So in this case, we are optimizing the acceleration instead of.
And in this case, yeah, we are penalizing the acceleration. We're giving it a weight, like we would like to minimize this acceleration. Anything you put in this objective function, remember that we are minimizing this objective function in the end, right? So anything you put in this objective, you are minimizing. And how important this term in your objective function to minimize depends on how much weight you put for that term in the minimization problem or in the objective function. Since acceleration here is not a direct control action, so like it's not an optimization, so it turns out that it will not be an optimization variable. So I can't put direct limits on the acceleration in this case. But I can penalize it. I can calculating the difference between the two speeds. This is somehow calculating the acceleration, right? So when I penalize this difference, turns out that I'm penalizing basically the acceleration, right? Or similar to penalizing the acceleration, because the acceleration is the difference in speed divided by delta t. Just penalizing the difference speed is some sort of penalizing the acceleration, right? Okay, any more question? Oh, I think, yeah, so so far we stopped here, right? I think we have some good time to do multiple shooting quickly. Yeah, so unless you have any question, I'll go forward. So what we did actually was a single shooting implementation. It was very intuitive, right? So we had this big prediction matrix X that we wanted to fill using the system model. So we filled it by the system model and the control actions, right? So what we did called the single shooting technique. So analytically, we said that, hey, our optimization variables are W, which has all the control actions from U0 to n-1. If we start from an index 0, then we stop at n-1, right? And then we got the prediction for X by propagating this U and the initial value for X. And we got this big matrix X, if you remember, right? We got this matrix F, where the initial vector in this matrix X, I'm calling here F again, so sorry for changing the variables names. The first entry in this matrix here is basically my initial condition, right? So this big matrix X is mainly function of what? W, my optimization variable, and some other constants or parameters, right? So my NLP problem, or the nonlinear programming problem, was that I wanted to minimize this objective, the objective function that is function of the prediction of X, and apparently the optimization variables. This is my cost function, right? And this is another way of looking at it, subject to some constraints, right? So here the objective function phi is function of the prediction, which is already a function of what? Optimization variables and the optimization variables themselves, right? And the constraints that I used here, I put the constraints on X and Y, right? But X and Y were already expressed in terms of what? The optimization variables, right? So we had inequality constraints. We had constraints on the map margins, and we had constraints on the control limits themselves. But did we have any equality constraints? So far, no. We didn't have any equality constraints, right? So what's the main drawback of single shooting technique? It's the nonlinearity propagation. So you remember how we filled up this prediction matrix, and you can imagine how nonlinearly the last entry could get if the prediction horizon is really long, like 10, 20, hundreds. So that can get really, really nonlinear. So this nonlinear propagation is reflected on the computational time is reflected on the convergence in general, like it may not converge for a really large prediction horizon, and so on, right? So the single shooting technique means that the NLP problem was discretized only in the control actions, where we wanted to have this equality between the state and the predicted state only at the initial condition. And the rest of the prediction was a forward recursion of this initial state. Right? That's single shooting. We have this equality only at a single point. That turns out to be a shooting point. If you want to like go and check more theoretical details. Right? Right, so then single shooting worked fine for us, right? But we can actually do better than just that, using the multiple shooting. So multiple shooting is another way of expressing or of converting or discretizing the OCP or the optimal control problem to a nonlinear program problem. So what we do in a multiple shooting method or a multiple shooting technique, we consider both U and X as optimization variables. So the optimization variables are not just U, they are X as well. Of course, this will be reflected on how we formulate the NLP later, but this is the first thing to note. So we have X as an optimization variable and U as an optimization variable. This means that we have more optimization variables, right? Just keep that in mind, right? And then we add a path constraint. We will have an equality constraint, which constrains the difference between the predicted state, the actual state and the predicted state. And the difference between the two, that's basically my model. So the difference between X and f of X should be 0. And we apply this at every prediction step. So that's why it's so applying this constraint or equality constraint at every prediction step or every shooting step, that's why it's called multiple shooting. Okay? When we see how this is coded, it will sink in immediately and it won't be any problem. Like there will not be any problem then, right? So now my optimization variables again are not only U's but also X's. So when the optimization variable was only U and we had a prediction horizon of 3, and we ended up with how many optimization variables? 6, right? So now if we additionally have X's, just keep in mind that X's, we have one more prediction in X than in U because one U tells me what the next X is, right? But the current X doesn't necessarily tell me what the next U is. Right, so that's why the length of X is normally one step longer than the length of U, right? So now we have more optimization variables, right? Okay, and then we will minimize our objective function, which is directly function of U of W, and instead of being a function of W. So now our objective is directly function of W because W has both, has the predicted state and has the control actions, right? And we will have these two types of constraints. We will have these constraints in equality constraints like map margins and control limits, and we'll have now equality constraints, which is satisfies the system dynamics. Right? So let's see how this is coded. But before that, let's look at some advantages of multiple shooting. Multiple shooting is actually called a lifted single shooting, and lifting means that reformulating the problem in more variables in order to get us like a convergence faster. It's a way of simplification. Looks like making things complex, but it actually simplifies things. Its performance is much superior than the single shooting because of lifting. And now we can, instead of initializing only U, when we solve MPC recursively, we can also initialize what? X, right? And this is an advantage, by the way. So think of single shooting again. What is the only thing we can initialize? U, right? But normally, we can know how the robot will move like, but we are not necessarily familiar with how the control action will look like. Like if I would like to initialize the control actions with some known trajectories, I have to solve the dynamics over that trajectories inversely, like I do inverse dynamics to get the control actions that satisfies this motion profile, right? And initialize my controller with this motion profile. But now, with the luxury of having the state as an optimization variable itself, so I can take the proposed initialization for x and plug it directly to my initialization. A little bit unclear, or maybe needs more clarification, but this turns out to be an advantage of having a multiple shooting discretization for the optimal control problem, right? The drawback might seem to be having a larger nonlinear programming problem, but it turns out that it's more sparse, and this means that it can be solved faster, and the conversions can be achieved as well, right? So let's go ahead and do multiple shooting. So what we have so far is very common to what we have or what we had earlier, right? Defining the sampling time, prediction horizon length, margins, symbols for x, y, and theta, symbols for v and omega, the right-hand side, the same function f, the same matrix u for the controls, the same vector p for the parameters, the same matrix x for the predicted state or the state prediction, the same q and the same r, right? So now let's compute our objective and the equality constraint which represent the dynamics. All right. Previously, what we used to do, or in the single shooting, what we did was we filled up this matrix x by propagating u and the parameters p in the system model, right? This is what we did earlier, right? Now we're not going to do that, right? So what are we going to do now? We're going to, in parallel, calculate my objective function and these constraints entries, right? Again, the first entry of x is my initial state, right? So my first constraint is going to be the difference between this initial state and the first parameter and the first three terms in the parameters vector, right? And then we go through this for loop, and in this for loop we calculate the objective. So you can see here that the objective is calculated directly from x, and x, like we did not change anything in x. It's the variable x as defined. Like we did not fill this x with anything. We're just putting x here as defined, right? And we're calculating the state st from x. We're finding the difference between it and the reference, p from 4 to 6, penalize it, add the penalization for the control, right? So there's a step that we didn't do here and we did in the single shooting, which was filling up this matrix, this big matrix x. We did not do that here. But instead, we filled up this vector g with the difference between the state, like the next state, from the vector x, and the predicted next state, which has, which by evolving the current state and the current control in the right-hand side of this equation, multiplying it by delta t and adding this up to the previous state. If you look at this like for 10 seconds, you will make sense of everything pretty much in this for loop, right? So what we're doing here is we are building up my objective and we're filling up my constraint vector here, right? So we would like to ensure this equality constraint at all the shooting steps. That's why this is called the multiple shooting technique. Okay. So again, the main difference in coding from x here and previously before calculating the objective, first we filled up the big matrix x by forward recursion of the system model and the initial state, right? But here we're not doing that. Here we're using x as an optimization variable itself. And instead, we're creating a constraint, an equality constraint between x, the optimization variable, and x, the predicted value of it, which comes from the model. Right? Okay. So now the optimization variable is longer. So instead of having only instead of reshaping only u, now we're reshaping x as well. So now this optimization variable vector will have like many values. Of course, it depends on the prediction horizon length. We're using the same structure for defining the NLP problem, the same fields, the same options for optimization, and now the constraints. If we look at the constraints, remember in G, what do we have in G? These differences, right? What is the upper bound and the lower bound for all these terms? Upper bound is 0 and lower bound is 0. This is as an equality constraint. So upper and lower bounds are zeros basically, right? Okay. So when we define our arguments, so the upper bound and lower bound for this vector are zeros, right? And look at the length of this vector. It's from 1 to 3 times n plus 1. N plus 1 because that's my prediction horizon, and 3 because 3 states. Like every shooting step has 3 states, right? Okay. Okay, let's go backwards one step. So what do we have in the optimization variables? The first part is what? The state. So we should put upper bounds and lower bounds on the states, right? And we will use the map margins we have, 2 and minus 2 for x and y. So we did that for x and y. And for theta, the upper bounds and lower bounds are basically infinity. Theta is free to be chosen, right? And the remaining terms in the upper bounds and lower bounds of x, which are my optimization variable, because now my optimization variables have everything, right? They have the x's and the u's, right? So and then we put the v min and max and omega min and max, right? And then the simulation loop, right? So the simulation loop is like before, except for the initialization. So the initialization here, we have initialization for u and initialization for x as well. So the initialization for the control actions over the prediction horizon is zeros, and the initialization of the x or the state trajectory over the prediction horizon is basically a repetition of the initial state for the all time steps. Well, it turns out to be zeros as well because the initial state was already zeros. Okay? All right. So now my overall initialization of the optimization variables is this big vector here, which has the initialization for the states and the initialization for control, because they are all now optimization variables, right? Calling my solver means that I have now the control actions. The nice thing about multiple shooting as well is that it doesn't give you the control actions, it also gives you the predicted trajectory, right? Because it's part of the solution is the predicted trajectory, right? So that's why here I'm extracting from x, which is the solution, the control action, and I'm also extracting the predicted trajectory. That's the controls only, and that's the predicted trajectory or the solution trajectory, right? And then applying the shift function as previously, and everything else in this slide is as previously. So now let's look at a Matlab demo for multiple shooting. Okay. All right. So now I'm going back. Yeah. I'll bring up Matlab again. I'm just going to do single shooting, just one step before doing multiple shooting. I just want to show you something before going ahead. So I'm setting back my reference orientation to be 0 again, right? So let's run this and see the average computation time per time step of the MPC, right? So here MPC worked fine for n equals to 10, yeah? And the average MPC time was 24 milliseconds or 25 milliseconds, right? That's not bad. So let's look at multiple shooting. So I'm going to set this to 10 again. Just want to make sure that the reference is 0 as well, okay? Okay. So now that's multiple shooting in action for n equals to 10. Works fine. But let's look at the differences, especially in time, or the computation time between the two, single shooting and multiple shooting. Here, this multiple shooting finished that in, again, around 24 milliseconds, right? Pretty close, right? So let's look what happens if the prediction horizon is really long. So let's go back to single shooting. And set my prediction horizon to 100. So 100 means how many optimization variables? 100 times 2, right? 100 times 2, 200, right? So it's going to be really slow at the beginning, right? So let's look at the average computation time per sampling step. So it seems like it's actually really slow. And the computation time turns out to be 230 milliseconds, or 0.2 seconds, 0.23 seconds. So that's quite time consuming, right? So let's do 100 on multiple shooting and see what happens. That's 10. That's multiple shooting. Oh, that's not even 100 milliseconds or even a 50 milliseconds. So that's let's say this is a 50 milliseconds and the other one is 250 milliseconds. So this multiple shooting is actually 5 times faster for this pretty long prediction horizon length, right? And that's not the only advantage. The other advantage could be in single shooting for even larger prediction horizon, the solver may not be able to find the solution all over or like at all, okay? So multiple shooting. So now when this was set to 100, how many optimization variables we have in this problem now? 500, yeah. We have 5 optimization variables times n equals to 100. We have actually not only 500, 503, right? Because of that, right? So we have 500 optimization variables. So compared to 200, and 500 was quite faster. So it's not only that you need a good solver to solve for an MPC problem, you also need a good formulation for your problem. And it turns out that multiple shooting, and I personally use multiple shooting more than single shooting. Actually, after knowing multiple shooting, I did not go back to single shooting again. And the reasons are so obvious, right? I think stopping here is a good point to stop at. And tomorrow we will talk about the rest of MPC stuff, which is basically how to include obstacle avoidance in MPC. And this turns out to be just adding more state constraints or constraints on the state. And then we will see how to implement MHE, right? So